So let's say I have some mega blocks, and I have little kids, so I have a billion mega blocks. And we can use these mega blocks to represent reactants in a chemical reaction. Now, what could they do? Well, if these are like atoms, they could form together to join a larger molecule, or we could break them back apart. So there's really two reactions that we're considering, right? If we take the reactants and we join them together into a larger molecule, then that's showing this reaction here. And that would be like an addition reaction. If we take them apart, then I'm doing the reverse of this, right? The reaction is going backwards, so I'm taking this apart. We could represent it by turning the arrow like that, or we could represent it as a reaction like this, or a decomposition reaction. So we have two reactions really. And in reality, just like the mega blocks can be put together in an addition reaction, they can be pulled apart in a decomposition reaction, they can go either way. In chemical systems, many chemical systems are the same way. You can build a bigger molecule, you can pull that molecule apart, or you can do a reaction one way and then you can do a reaction the other way. And if I have a reaction system that can go both ways, in reality, it actually will be going both ways. So if I have a bunch of mega blocks sitting in a container, some of these, so this is now my reaction vessel, as they bump into each other, some of these mega blocks will be forming like this, and some of the mega blocks will be coming apart. And so in my system, both of those processes actually will be happening at the same time. So I can represent that with a different type of reaction arrow. So if I say that these two reactants here can form this product, but this reactant can also form these products, then I can use this arrow here. And this funny double-headed arrow is called an equilibrium arrow because it's used to represent a chemical system that exists in a state of equilibrium, of chemical equilibrium. And what chemical equilibrium means is that if I have a forward reaction, which is the forming of these two blocks, and if I have the reverse reaction, which is the coming apart of these two blocks, both of those processes would be happening simultaneously, so at the same time, and at the same rate. Both of those things must be true for the system to be at equilibrium. And so if I wanted to represent that here, right, one of my hands could be the forward reaction. So my right hand is going to put reactants together to make a product. And my other hand is going to be the reverse reaction. It's going to pull products apart to make the reactants again. And if my system is at equilibrium, both of those things are happening at the same time, and they're happening at the same rate. So every time my one hand puts a pair together, my other hand is going to pull a pair apart. So the concentration in my container here stays the same, right? If I have two moles of these reactants and I have 1 mole of products, as long as I keep doing these two processes at the same rate, so every time I put one together, I take one apart, even though my reactions are both still happening, my concentrations 2 and 1 are always going to be the same no matter when I stop this. Right? Anytime I glance at my equilibrium system, the concentrations of reactants and products are going to be the same. And even if I bring more into the mix, so now I've got 4 moles of these reactant molecules and 2 moles of product molecules, as long as every time I pull one of these apart, I put one together, then my concentrations 2 and 4 are never going to change. Anytime I stop, I'll always have 2 moles of products and 4 moles of reactants. So let's look at this in terms of chemical entities instead of megablocks. What I need to start out with is a closed system. We can't have reactants or products being able to enter the system, or they can't leave the system. Once they are there, they are there. And if that's the case, then when my reaction comes to the point where there are no observable changes, I can't observe the formation of more products or more reactants, then my system is in a state of dynamic equilibrium. So the forward reaction, the rate of the forward reaction is equal to the rate of the reverse reaction. So we assume that they are not stopped, but they're happening at the same time and at the same rate. And I can have dynamic equilibrium like this existing for a chemical reaction, like the above here, where the sodium sulfate and calcium chloride are reacting to produce calcium sulfate and sodium chloride. So this is a chemical reaction. I can also have equilibrium existing for phases. If I have a container with water and there's liquid water on the bottom, there's water vapor on the top, once it seems like the evaporation or the condensation has stopped, there's not any more water leaving the liquid phase and entering the vapor phase, or vice versa. In actuality, there still is water evaporating from the beaker, and there is still water condensing, but the evaporation process and the condensation process are happening at the same rate and at the same time. So the system is in equilibrium instead. Same thing if I have a solid that's dissolved in water. Maybe I've dissolved more solid than the solution can hold. So I've gone past the solubility. So now instead of just having a nice, clearly dissolved beaker, I've got a pile of solids sitting at the bottom of the container. And there's no more of this solid dissolving, or I should say, the pile of solid doesn't get smaller, and the pile of solid doesn't get bigger. Now, at first glance, it would seem that the solid has just stopped dissolving, but just like in these other cases, there still is solid dissolving, but it's that this forward dissolving reaction, or this forward dissolving process, I should say, is equal to this reverse crystallization process. So here's a really simple example. I've got hydrogen iodide being formed from hydrogen gas and iodine gas. So as these molecules react with each other to produce hydrogen iodide, the system is in a state of equilibrium. So if I add at the beginning just iodine and hydrogen, then they're going to start to collide with each other to produce some HI molecules. So here's are some hydrogen iodide molecules that are forming. And early on, though, I would have more of this forward reaction than I would have the reverse reaction, because I don't have very much of this product yet. But as the amount of product builds up, then the reverse reaction is going to speed up as well. I'm going to have more reverse reaction happening until finally the rate of the forward reaction and the rate of the reverse reaction are equivalent, and at that point I'm in a state of dynamic equilibrium. So we could measure the system in a few different ways. We could start by doing what we did above. We could take all reactants, and I'm going to add no product at the beginning. And over time, the reactants are going to be used up. Not completely, but they're going to be used up, and my product is going to be produced until I get to a point of balance, until I get to a point of equilibrium. And this is what this graph shows over here. We're going to see lots of these graphs like this. So here's my reaction. I see I've got my reactant 1, my reactant 2 over here. I started with a lot of those, and they were consumed over the course of the reaction. Initially, the slope downwards is very steep, which means they're being consumed very quickly. And my product here is being produced. So I started with no product. I started with 0 product down here, and I gradually produced product here. Now, I could have also taken the system and start with no reactant. Or maybe we want to test it. Maybe it's not equilibrium at all. I'm going to start by just adding a bunch of product and see what happens. And in fact, in this case, the product is going to be consumed, and I'm going to produce some reactant until I get to the state of balance again, to the state of equilibrium. And I could start with a mixture of reactants and products, and again, I would get to a state of equilibrium. I would get to a state of balance over time, until the point where, again, the rate of the forward reaction equals the rate of the reverse reaction. So in my graph here, we could find the point where dynamic equilibrium was reached. So where was equilibrium reached here? Well, if equilibrium is reached at a point where my forward rate and the reverse rate of the reactions are the same. So that means that my amount of reactant and my amount of product aren't changing. That means that these lines have to be level. And they're not level until maybe about here. So maybe at this time here, I can draw a straight vertical line. This time here is when I would say that equilibrium was reached in this reaction. And we might give you a graph with a time scale on it. So maybe this is 5 minutes. 5 minutes in, this reaction reaches equilibrium because my overall quantities of reactants and products aren't changing after that point. In previous labs, you've calculated percent yield. Percent yield is the way that we can identify how much of a product forms relative to how much product we think should form. And so if I have a system in equilibrium and it forms 78% product, that means that 22% of my reactants remain as reactants. And the 78% is going to form the product over here. So my percent yield can be a useful way to figure out the position of the equilibrium system. Does it produce more products, or does it produce few products and remain mostly as reactants? We could calculate this theoretical yield just using basic stoichiometry. And so based on the percent yield, we can classify systems in one of these categories. If a reaction goes essentially 100%, we would say that the reaction is quantitative. And then we could use the regular plain Jane reaction arrow that we've used before. We can use this basic reaction arrow here because we just say it basically just goes. But if I'm using an equilibrium arrow like this, then I can identify usually where does the position lie. If the reaction goes greater than 50%, so more than 50% of my original reactants end up as products, then we would say that the reaction is products favored. And on top of the equilibrium arrow, we can specify that the reaction goes greater than 50%, right? Greater than 50%. If the reaction does not go very much, it produces some products, but it's less than 50%, then we could say that it's reactants favored. And above the reaction arrow, we could write less than 50%. And finally, if a reaction doesn't go to any appreciable degree, it's an insignificant amount of reaction that happens, then we could say that the percent yield is negligible. It is a potential reaction that could take place, but under the current conditions, it's not able to happen. And so then the reaction is non-spontaneous. There's no apparent reaction. So we can use these terms products favored, reactants favored, or quantitative. These are the main three that we'll use. Now we're going to have to do a little bit of math when it comes to equilibrium systems. And one of the ideas that's going to be very helpful for us in doing those calculations is the idea of the equilibrium constant. The equilibrium constant is a value that allows us to make judgments about an equilibrium system. Is it more reactants favored? Is it more products favored? And it's going to allow us to do calculations. To figure out the equilibrium constant, we need to create first what we call an equilibrium law expression. And the equilibrium constant is calculated by the equilibrium law expression. So the equilibrium constant here is the Kc. And this whole thing is the equilibrium law expression. Now, how do we calculate it? Okay, so we have a generic chemical reaction. These are my two reactants, and these are my two products. So I have reactant A, reactant B, produce product C, and product D. Now these lowercase letters in italics, those are the coefficients. So my coefficient of reactant A, my coefficient of reactant B, my coefficient of reactant C, my coefficient of reactant D. Now to build this mathematical relationship, I need to take the concentrations of my reactants and products. These square brackets that you see down here, remember that stands for concentration. So I need to take my concentration of my products. Now, each of those concentrations is going to be taken to the exponent of the coefficient. Okay, so whatever my coefficient here, if I have a coefficient of 2, I will take this concentration to the power of 2. Same thing with this product here. And then I'm going to divide this by the same thing for my reactants. So my concentrations of reactant A and reactant B divided or taken to the power of their coefficients. And when I calculate that mathematically, the number that comes out will be my equilibrium constant, my Kc value. And we can think about this, right? Products are on the top, reactants are on the bottom. So if I have a lot of products, if my concentration of products is high, that means I'm going to have a large number on top of a smaller number. And that's going to give me a Kc value that's greater than 1. So if a Kc value, an equilibrium constant, is greater than 1, that means that the reaction is products favored. If I have more reactants than products, then I've got a smaller number divided by a bigger number. Well, that's going to end up being a decimal, or a number that's less than 1. So in that case, my Kc value will be less than 1, and that's going to mean that my reaction is reactants favored at equilibrium. So these ideas here are going to be important, especially in a little bit. So just kind of keep this in the back of your mind. When we ask you to evaluate whether a reaction is reactants favored or products favored, you can use the Kc value in order to do that. Now, this just seems like a giant schmozzle, so let's use an example to try to sort it out. So if we want to write the equilibrium law expression for the reaction of nitrogen monoxide gas with oxygen gas to form nitrogen dioxide gas, what would that look like? Well, let's start by figuring out what the reaction is that we have. So the reaction is between nitrogen monoxide gas, NO, and it's reacting with oxygen, O2, to produce, I can use my equilibrium arrow here, to produce nitrogen dioxide gas. Okay, now I need to balance this because I can't move forward unless I balance this. So my nitrogens are balanced here. My oxygens, I've got 3 on the left, and I only have 2 on the right. So I can either balance it by doubling to give myself 2 nitrogens and 2 nitrogens here, or I can use a coefficient of 1/2. You would see that the Kc expression would come out differently, so sometimes we'll have to tell you whether we want you to balance with lowest whole number coefficients or if fractional coefficients are okay, but if we don't specify, you can use either. So then let's build the Kc. So my Kc law expression is going to be equal to my products divided by my reactants, each taken to the power of their coefficients. So I only have one product, my nitrogen dioxide, so it's going to go on top, NO2, and it would be the concentration of this, so it needs square brackets. And it's got a coefficient of 1, so it's taken to the first power. Well, we don't need to write that in, because that's not going to change the value. Then my reactants go on the bottom. So it would be the concentration of my nitrogen monoxide gas multiplied by my concentration of oxygen gas. And the oxygen gas will be taken to the 1/2 power. And these guys are multiplied by each other. So then this is my equilibrium law expression, my Kc. Now, let's look at that original example that we had. The value, my formation of iodine. So if I'm reacting hydrogen and iodine gases to produce hydrogen iodide, and we'll balance this with a 2 here. If the value for the Kc of this formation is 40 at some temperature, determine the value for the decomposition at the same temperature. Okay, now I'm not given any concentrations, so I can't do this mathematically. So let's compare the formation and the decomposition. So the formation would be this forward reaction. H2 plus iodine react to give hydrogen iodide. The decomposition would be the reverse, so we'll write it out backwards just so that we can really get this point. Now, why don't you pause it here for a minute and try practicing. Can you write out the equilibrium law expression for the formation and for the decomposition? and then once you think you've got it, resume and catch back up with me. We'll see if you're right. So the products go on the top. My hydrogen iodide gas would be taken to the power of 2 divided by my hydrogen gas multiplied by my concentration of iodine. Okay, so that's my formation. Now for my decomposition, my products go on the top. So my hydrogen iodide concentration would be multiplied by my iodine concentration. And that's divided then by my HI, taken to the power of 2. And what the question is telling us is that the value of Kc for the formation is 40. Now, we don't know the value here, but if you may be starting to clue into why we're writing all of this out. If you notice the mathematical relationship between the expression we wrote out here and the expression we wrote out here. So if you haven't noticed the pattern, take a second, maybe pause. Can you see what's the relationship between this expression and this expression? And so if you notice that what we've done is we've just flipped the fraction, we've taken the reciprocal when we've gone from the formation to the decomposition, and that makes sense because when I flip my reactants and my products, well, that just flips what's on the top and the bottom. So if my Kc value here was 40, then I would have to take the reciprocal here, 40 over 1, so it would be then 1 over 40. Or I could express it as a decimal as 0.025. And this is going to be an important little tidbit. So what's the relationship between the value of Kc for a reaction and the Kc for its reverse reaction? It's always going to be the reciprocal. So that means that if you know the Kc value for one reaction, you actually do know the Kc value for its reverse reaction too, because it's the reciprocal. Now, a couple of things here that we have to point out. Equilibrium law expressions do not include solids or liquids, and that's because their concentrations don't vary. If I have a solid chunk of copper and as the copper is consumed, the concentration doesn't change, but the mass of the solid chunk of copper changes. So the concentration isn't useful and it doesn't help me mathematically. So what I do is I just omit any solids or liquids when I'm writing a Kc expression. So here's an example here. If I want to write the equilibrium law expression for the decomposition of solid ammonium chloride, so NH4Cl, solid, reacts to give gaseous ammonia and gaseous hydrogen chloride. Let's check my balancing, it's good. Then this guy's a solid, so when I'm writing in my Kc, it just gets omitted. So my reactants go on the top, my ammonia multiplied by my hydrogen chloride. And this is all over 1, but that doesn't change the value, so I can just leave it like this. So this would be my Kc expression then for this reaction. And then also, if I have ions, they have to be written as single entities. So that means that before I can write a Kc expression, if I have a regular chemical equation that includes spectators, I have to break it down into a net ionic equation first so that I can eliminate the spectators. Spectator ions will not be included when I write a reaction. So if I have this reaction here, zinc reacts in copper chloride solution. Well, here I have to figure out what the reaction is going to be first. So I have some zinc solid, copper 2 chloride. That's going to react, it's a single replacement, so it's going to react to give zinc chloride and solid copper. So I need to write the total and the net first, right? So I have to do my non-total net. So in my total, anything that is an aqueous compound gets split up. So this guy is actually floating around as copper 2 plus ions and chloride ions. And there would be 2 chloride ions, right? Because we needed 2 of them in order to balance. And then on the right side, this guy is aqueous ionic too, so it's going to split up. It's going to dissociate in solution to give zinc ions and, again, 2 chloride ions. So remember a couple of things. People always, when they do non-total net, they like to give these solid entities charges. Does not have a charge. My copper is not charged. My zinc is not charged over here. It's just these ionic compounds because they are ions. They do have charges. We just don't write them when we show them as a compound. Second thing is I need to identify my spectators. So a spectator, remember, has the state of matter that stays the same and the charge stays the same. Both of those things must stay the same. So my zinc, its state of matter and its charge change, so it's not a spectator. Same thing with my copper, but my chloride, I had 2 aqueous ions, so this is a spectator, this is a spectator here. Those guys are gone. So then my net ionic equation is my zinc reacting with copper 2 plus to give zinc 2 plus and solid copper. And now I can write out the equilibrium law expression. So my products go on the top. Zinc 2 plus aqueous. My copper here is a solid, so it doesn't get included. And we divide by, again, my zinc is a solid, so it doesn't get included. It's just going to be my concentration of my copper ions. And this would be my Kc.